Welcome back to AI, from zero to researcher. In episode 2, we built the artificial neuron, a weighted sum, a bias, and an activation function that draws a single straight decision boundary. We saw that this works for some problems, but that XOR is impossible for any single line. Today, we break through that wall. Episode 3. Neural networks and representation learning. If weighted sum or decision boundary from episode 2 feel fuzzy, go back and revisit. Everything today builds on those ideas. Remember XOR? A single neuron can't solve it. But watch what happens when we stack two neurons and add one simple ingredient, a fold. That just worked. Same data, same goal, but a completely different internal geometry. The network didn't find a better line, it warped the space so that a line was enough. That idea, learning to reshape the space, is the single most important concept in deep learning. By the end of this episode, you'll understand exactly how it works, and you'll build it yourself in code. In episode 2, we built the artificial neuron, weighted sum, bias, activation. We saw that one neuron draws one straight decision boundary and that XOR is impossible for any single line. If weighted sum or decision boundary feel vague, go back to episode 2 before continuing. We use those ideas everywhere today. A neural network is what you get when you connect neurons in layers. The input goes in on the left. One or more hidden layers sit in the middle. The output comes out on the right. Each neuron in a layer receives inputs from every neuron in the previous layer, computes its own weighted sum plus bias, and passes the result through an activation function. Here's the geometry. Each hidden neuron draws its own decision boundary, its own straight cut through the input space. With two neurons, you get two cuts. The hidden layer's output is no longer the original coordinates. It's a new pair of numbers, how far each point is from each cut after the activation function. The data has been redescribed in a new coordinate system that the network chose. Add more neurons, get more cuts. The combination of those cuts can approximate curves, corners, and complex boundaries. But there's a catch. This only works if we add one critical ingredient between the layers. Here's a subtle but important fact. If every layer is just a weighted sum with no activation function, the whole network collapses. Two linear layers in a row are mathematically equivalent to one linear layer. No matter how many layers you stack, the result is still a single linear transformation. You'd be back to one straight line, no better than a single neuron. This is why nonlinear activation functions are essential. They're the ingredient that makes depth meaningful. The most common activation today is ReLU, rectified linear unit. It does one thing. If the input is negative, output 0. If the input is positive, pass it through unchanged. That's it. Geometrically, ReLU folds the space. It takes part of the input space and flattens it to 0 while leaving the rest intact. Each neuron folds along a different line. Stack multiple neurons with ReLU and the space gets folded repeatedly, like creasing a sheet of paper from different angles. Those folds are what create the complex boundaries that can solve XOR and much harder problems. In the next chapter, we'll watch these folds transform the data step by step, so you can see exactly how the network reshapes the space to solve problems like XOR. Other activations exist. Sigmoid squashes everything to between 0 and 1. We saw it in episode 2. Tanh quashes to between -1 and 1. ReLU became dominant because it's simple, fast, and avoids a training problem called vanishing gradients that we'll cover in episode 4. The specific choice matters, but the core principle is always the same. Nonlinearity makes depth meaningful. The raw input lives in the original coordinate system, x1, x2. The hidden layer maps those inputs to a new coordinate system, h1, h2. Watch what happens to each input as it passes through the hidden layer. Input 0, 0 lands near the center of the new space. Input 0, 1. ReLU kills one neuron and fires the other, so the point jumps up. Input 1, 0, the reverse pattern. The point shoots to the right. Now, input 1, 1. The fold brings it to the exact same spot as 0, 0. The two inputs that should be in the same class, 0, 0 and 1, 1, end up close together in the new space. The two that should be different, 0, 1 and 1, 0, land far apart. The network has learned a representation where the problem becomes linearly separable. This is representation learning. The network discovers its own features. You didn't tell it what to compute in the hidden layer. You just gave it the task and the architecture, and it found a coordinate system where the task becomes trivial. In bigger networks solving harder problems, this happens across many layers. Early layers learn simple patterns, edges, textures, simple shapes. Middle layers combine those into parts, curves, corners, strokes. Later layers assemble parts into evidence for the final answer. This looks like a 7. Each layer builds on the representation from the layer before it. This is the defining idea that separates deep learning from classical machine learning. In classical ML, a human designs the features. You decide that pixel intensities, edge counts, or histograms are the right inputs. In deep learning, the network learns the features. And often, the features it discovers are better than anything a human would have designed. There's a closely related idea called an embedding. Sometimes your input isn't a number, it's a word, a category, a user ID. You can't multiply cat by a weight. So instead, you assign each discrete item a vector of numbers, its embedding. These vectors are learned during training, just like weights. The network adjusts them so that items which behave similarly in the task end up with similar vectors. Words that appear in similar contexts get similar embeddings. Products that get brought together drift closer in embedding space. You may have seen the famous example, king minus man plus woman roughly equals queen. That's not programmed in, it emerges from the learned geometry of the embedding space. Embeddings will come back in episode 7 when we need to represent words for sequence models, and again in episode 11 when images and text share the same embedding space. The key point: embeddings are representation learning for discrete inputs. The network builds a continuous space where the geometry reflects the structure of the data. There's a deeper reason why representation learning matters, and it connects to a problem called the curse of dimensionality. As the number of input features grows, the space of possible inputs grows exponentially. A 2D space with 10 points per axis has 100 cells. A 10D space has 10 billion. A 100D space has more cells than atoms in the universe. Data becomes unimaginably sparse. Every point is far from every other point. This means that in high dimensions, you cannot just cover the space with examples. You need the model to discover that most of the variation in the data lies on a much lower dimensional surface, a manifold. Representation learning does exactly this. The hidden layers learn to project the data from a high-dimensional input space onto a lower-dimensional structure where the patterns live. This is why a network with 100 inputs and 10 hidden neurons can still work. It is finding the 10 directions that actually matter. Let's build a 2-layer network from scratch. No frameworks, just NumPy, and train it to solve XOR. 4 parameters in W1, 2 in B1, 2 in W2, 1 in B2, 9 parameters total. That's the whole network. Now let's train it. The loss drops from 0.75 to nearly 0. Let's check the predictions. XOR solved. A single neuron couldn't do this at all. Episode 2 proved that no line works. But 2 hidden neurons with ReLU and 1 output neuron get it right. Now the important part, let's look at what the hidden layer learned. Look at that. In the original space, XOR points are tangled. No line works. But in the hidden space, the network rearranged them so that a line cleanly separates the 2 classes. The hidden layer invented a coordinate system where the problem is easy. That's representation learning. Not a metaphor, actual numbers, actual geometry. One hidden neuron computes z equals w1x1 plus w2x2 plus b, then applies ReLU, h equals max of 0 and z. On one side of the neuron's boundary, the output varies. It carries information about where the point is. On the other side, everything gets mapped to 0. That's one fold. The second neuron folds along a different line. Now we have 4 regions in the input space, each mapped to different combinations of H1, H2. Points that were impossible to separate in the original space are now in clearly different positions in the hidden space. Folds. That's all it took. The output neuron just draws a straight line in this new folded space. Easy. This is what depth and nonlinearity buy you. Each layer folds the space. Each fold makes new regions distinguishable. Stack enough folds, and you can separate almost any pattern. Here's the what if experiment. What happens if we remove the nonlinearity? Replace ReLU with the identity function. Just pass the values through unchanged. The loss is stuck at 0.6931. That's the loss of predicting 0.5 for everything. The network can't do better than a coin flip. 2 linear layers with no activation are just 1 linear layer, and 1 linear layer can't solve XOR. We proved this in episode 2. The nonlinearity is not optional decoration. It's the structural reason neural networks can solve problems that linear models cannot. Without it, depth is an illusion. Let's compress what we covered. A neural network stacks neurons into layers. Each hidden neuron draws a straight cut through the space. Nonlinear activations like ReLU fold the space at each cut, making depth meaningful. Without them, the network collapses to a single linear layer. The hidden layers perform representation learning. They transform the input into a new coordinate system where the task becomes easier. Embeddings extend this idea to discrete inputs, mapping words or categories to learned vectors in continuous space. We saw this concretely. 2 hidden neurons with ReLU reshaped the XOR problem from an impossible tangle into a clean linear separation. The network didn't find a cleverer line. It invented a space where a simple line was enough. One important research habit: do not confuse expressive power with guaranteed good generalization. A network that can represent any function can also memorize noise. Capacity is necessary, but not sufficient. Evaluation on unseen data, which we'll cover properly in episode 5, is what actually tells you whether the learned representations are useful. We built a network. We trained it. It learned representations that solved XOR. But we glossed over something: the backward pass. Those gradient lines in the code, DW2, DW1, DHH, where do they come from? How does the network figure out which of its 9 parameters to increase and which to decrease? That's the question for episode 4. Loss, gradients, and backpropagation. We'll see how the network measures its mistakes, how it traces those mistakes back through every layer, and how one of the most elegant algorithms in computer science makes this efficient enough to work with millions of parameters. And here's a question to carry forward. We use 9 parameters to solve a problem with 4 data points. What happens when you have more parameters than data points? That tension between the power to represent anything and the discipline to learn something useful runs through the rest of this series.